And live. Okay, so this afternoon I implemented a vector quantized variational autoencoder, and this is the nightly stream. I'd like to take this VQVAE and instead of using a convolutional deep network, not so deep but a few layers, I'd replace it with one convolutional layer and put some transformer blocks both in the encoder and the decoder. See if it makes the image quality better. I definitely didn't train this enough. So we can get much better results. And from 512 codes in the codebook, approximately used only 101, so pretty much more to go in terms of training. But I'm not going to spend the night waiting for this to train. Instead, first and foremost, I need a data set. I have this faces data set, and I'm making a 64 pixel version of it. So the training data set should have 5,370 samples. Yep. Well, it's actually one more because of zero indexing, but whatever. So the rest is the test set. So this finished copying. Now I can upload it. This is data sets / faces 64. Give credit to the author of the original faces dataset that had really big images. I need smaller ones for training, so I'm just resizing them and uploading to Hugging Face. This doesn't look right. So I think it's not cached here. The argument will be data dir. Yeah, it's data dir. So we can stop this upload. And I will just re-upload it. Now it looks better. Yep, it's up on Hugging Face. Let's save the state of the notebook. So this one, and I will base my implementation from this. I won't re-implement everything from scratch this time. It's gonna be this. So let's just use 64, batch size 65, we can up it, I think, 256. Okay, not sure if we need this function anymore. And nope, so I will follow kind of the DeepMind paper, the Gini paper. This one. Oh, so this one. To make the video tokenizer. And the configuration can be seen somewhere, maybe in the appendix. Yes, video tokenizer training. Well, I don't have this kind of hardware, but the dataset is much smaller and we're not working with ST transformers. It's going to be just a latent image based transformer with a fraction of the layers. The decoder is much heavier. Cosine decay for the weights and with warm-up steps. Now they create patches from the images. Patch size of 4, meaning 4 by 4 patches in 512 latent dimensional space. So first, let's not forget to change the optimizer. And even before that, I want to keep track of the total number of epochs, because I'm rerunning this block multiple times. So that's going to be the global epoch counter. Start from 0, and if I no plus plus in Python, I don't like that. Okay, optimizer Adam W. The learning rate for them was set to 3e minus 4. Maybe because it was training for a long while, so bumping up the learning rate might help with that. And I can always lower it. Now the weight decay. Cosine decay 1e on the minus 4. And what was AMS grad? It's from the paper on the convergence of Adam and beyond. An AMS grad version of it. The DeepMind paper doesn't mention this one. Obviously, I know just because I set the parameters similar, I have a different data set. It's absolutely dependent on the case, almost. So this is just for like a rough guideline. So 64, I should rename this image tokenizer. And it will have a bit different parameters than the VQVAE. So no channels anymore. Let's just start from the encoder and then we will change the parameters. So, new code block 4. I'll need an attention, a multi-head attention, a feed forward layer or block, and I might need to pull up the paper. So it's a softmax Q by K transpose over square root dk softmax times V and multi-head is just concatenating the heads where heady is this. Now, in this case, I won't need a triangular mask like for GPT. I'm not sure if I can implement the multi-head attention from so we only need this one. Don't need mask. And positional encoding for images. If I create those patches, I definitely need positional encoding. It's gonna be interesting to find out how. Because let's say I have one convolution block here. In channels is 3. And the out channels would be D. And D 512, numheads 8, because this adds up to 512. So that's D. And the kernel size, so I need 4 by 4 patches. Now the stride, I mean, they say they split it up to 4 by 4 patches, but is there any overlap? The video tokenizer itself is 200 million parameters. I'm having trouble training a 4 million parameter model. Well, not trouble, but it's slow. Okay, so that's not the same as embedding size 32 and 1024 unique codes. So that's going to be 32. And the codebook size. .32 is set to D already. In size, it's just 64. No channels parameter. This code block is just to test out if the implementation is correct. This is the actually used model, and well, I'm gonna just try with codebook of size 500 for now. No channels parameter. I mean, I could have a number of like n layers. It's the number of transformer blocks, not actually layers, but and we just be symmetric. In this case, they use more for the decoder, but for now, keep it simpler. Won't need a residual downsample block. Same for the decoder. And I'll need a transformer block. With num heads. So assert that yeah, and not really needed this one. I need 2-layer nars, that is for sure. The normalized shape. It's later then. So there's head dim and num heads. And what I have here, let's just check the size of this. Yeah, so I was so supposedly they trained the model on 96 by 96 pixel images, but I don't see any mention of that in the paper. So 96 times 4, that's 9, yeah, that's like 24, and in that case there's no overlap between the patches. That's what a stride 3. Stride 1 step, yeah. Stride. So step 1, 2, 3, stride 4, and with no padding. So this should yield D, and in our case 16. and here we'll have some transformer blocks. That take in BD 1616. Squash it like this and and permute. So back to the paper, not this one, not this one, this one, but only this part. 2 layer noms, 1 feed forward, linear softmax, and of course this is all with residual. The multi-head concat. So we have an embedding dim but on 4x4 patches. I think this was it an embedding or a linear? I think it was, I mean it's a matrix. So yeah, first linear projection to dv. So we have the embed dim D, and dk and dv. Now this is a linear layer then from embed dim to dk. The keys are the same and the value moves from to the VQVAE. In this case, obviously the patches contain 16 pieces of this d-dimensional vector. So this must come in as batch d, where T is basically H by W. So this assumes batch H by W D. So but here we project it. D model dk. So D model, this means this is the matrix for the linear layers. These we need separate Q, K and V. That's just so another 3 embedding. I'm just gonna go with that. Maybe I'm totally wrong, but so there's Q and then dot embedding DD. Oh. K and V. And this doesn't require a bias. Yep. So now, first, if I project this, that's just gonna be the multi-head. It's self-attention. Anyway, but so if I project or it's each of these projected versions, queries, keys, and values. We then perform the attention function in parallel, yielding dv dimensional output values. I mean, I could project like so that query x but that's it projects to dk. I'm going to ask for help. I implemented this like once or twice a few weeks ago. So I'm going to refer to Andrei Karpathy's GPT-2 video series implementation. Here in this Python file. Yeah, there's no embedding, but then so Q will be the projected X, so that's the matrix itself, but so it bias true. Maybe. No, actually bias needs to be false, and I was right. But I don't need the mask right now because it's not temporal, so, and it's really simple. No, this isn't even needed. So 3 linear projections. Well, it's one variable here, but on the paper it's dk, dk, dv. Here is the lower triangular mask, soft maxed up to because this is infinity, where it is 0, and then this will turn it to 0. And with multi-head you just concatenate it and project h in self.heads. But I also want to log everything as I go. So yeah, this can be large Q key self.key X, and I misremember because there's no other matrix. This will be the matrix, and from embed dim to dk, and this time I would like to maybe just put an attention block right here. Or head, so the head dim will be, this needs the D as well. This D where num heads, we need to assert that D mod num heads equals 0. And that D num heads is greater than 2. So the self.heads will be an module list of attention blocks with D, and in this case let's pass head dim and head dim. Num heads and we need a projection, but no layer norm here. That's a linear module from D to D, I guess. And x equals stores.cat hx for age in south.heads. But this projection then goes from, because if this is concatenated, this will be d times num heads, I suppose. So x equals south.project x and return x. So here we have num heads. Only thing I want to do is print the shapes here first and build from there. So I don't really want to try to implement from my head without seeing the shapes. So definitely multi-headed tension. And there are two layer norms, DD I'm just not sure if I also have not just batch size but D and D, so then this will only work, this will work separately on each element in every T. X equals x plus south.mha south.ln1. We normalize it first, and there's gonna be this feed forward block here that can be just an nn.sequential and I would want the shape, and this is ln2. I won't do this now, just return x. It's gonna be maybe nn.linear. So multi-headed tension projects it back to D. Mosquito. So nn.linear, I guess from D to D, put a galloon there. Normalize and drop out. D. Maybe a dropout, but not now. D is D, num heads is num heads. And all I want now is to have an encoder and just try it out like this, even in a simpler way. Yep. Okay. So let's take, no, actually this here, just encode something, encoder, and y-hat, okay. To D, there's no D. Let's move up the device here. Also, torch.manual seed. Okay. Yes. Well, nope. So, no channels, no insides. So there's D. And I'm gonna put a transformer block. Dropout, yes, we can pass the dropout. Set to 0. And that's gonna be D and num heads, so I need D, num heads, D, num heads, and basically and number of num layers for range num layers. Transformer, it takes 3 positional arguments, but 4 were given. D num heads drop out. I'm not sure I understand. Maybe I just need to rerun this. Well, the encoder now, D. Just 1 layer and num heads 1 and 1 layer. D. Well, what was it? 32 for them in Gini. $1,024. But the video tokenizer training, the model. The codebook's latent dim was 32, but we are far away from that. KQ size, this is 64, so 64 is the head dim. So the D here, Vietnam heads 8, T model is 512 in case of this, and for the vector quantizer it will be much less. Even without this, let's just try print y hat dot shape. That's, yeah, because that maps it up to 5, 12, 16, 16. That's about right, 16 by 16 grid of patches. Now the transformer block, just need a comma here. Yes, absolutely. So this happens in layer norm, and because this X must be BTD, I guess, and we need to permute reshape. So this is the form we need, and this comes in as B, D, H, W. So the output to the vector quantizer should be BDHW, so we will have to convert back, and basically this is the thing that we need to do here as well to work with it. So that's our final shape that we need. I'm gonna call this it's latent already because there's that convolutional layer, but let's call this Z here. So I take X, permute it, batch stays at the same position, then I take index 0, 1, 2, 3 and 1. We need contiguous memory and view it as, let me just extract the shape, x.shape. We need a continuous view. Batch, now T will become H by W and D. And we work with Z's here from then on. And now since we attach these transformer blocks, I'm not even sure, probably I should just convert it here. So instead of this sequential model, I will do it manually. I could have a module list here or just make this as a like conv, then self.blocks. Now that's a module list, and that's not needed yet. So I don't have a net anymore, but I can say self.z, not self.z, just z. Self.conf x, and now this will has this shape. I can take z.permute, this will convert it. And for b in self.blocks, z equals bz, then we project, well, we shape z back to its original. So now z is in the shape of btd, transformer block won't change its shape, so this comes actually, it was b h w d, and we squash the h and w to t. Now this stays the batch as before, but we take d h w and view it. Actually it's btd, so I take 0 to 1 as continuous and view it as bhwd, return z. Now here I don't need to convert it anymore because already receiving it in this shape, btd. Let's see what the layer norm says now. Tuple is not callable, that's for sure, because of the comma here. It's invalid or input size. Okay, which permute? This is the first permute. That's x, that's z dot shape. Cannot access local variable z. Yes, because now this is x. Expected tensor as element 0 in argument, but got none type. What's the 256 here? Our latent dim is 512, and the 256 is 16 by 16 by dk becomes the head dim. Num heads is 1. Surely 1, surely 1. Two 56 is so that's 16 by 16 times 4, because we have this many pieces and kernel size is 16. Yeah, that looks fine, as it did before. And Q's shape so that's 512 and dk. Since both are head dim, I could also just use head dim here for simplicity, but no. Head dim is also that one. 16 by 16 itself is 256, so that's just H by W, because I'm an idiot. So this looks fine, because that's the T, and that's the D. And of course we can multiply these to have 1, 256, 256. That is to represent the relationships between each of the latent vectors. But before doing that, do I have anything else to do? Well, head dim is just fine. Squashed it. Yeah. I wanted to print the shape of this one. Because it's a layer norm D. And that shape. Not ln itself, just the shape. So that's 1, 256. It's the same, so it just normalizes it. It's a layer norm. If a single integer is used, it is treated as a singleton list, and this module will normalize over the last dimension, which is expected to be of that specific size. So this layer norm actually only normalizes these for each t. That's good. And now, since these are the shapes, now where are the shapes? I didn't print. What's the issue now? Input must be tensor, not torch. Something here. Because that's going to be, yep. One more thing, torch.cat, and it got non-type, because I don't return here anything. So let's actually implement. So because this maps to dk and to dway, these both will be bt dk, bt dk, because the linear module in features out features. So this is just xa transpose plus b. Yeah. So right now this is just a matrix multiplication xa t, so let me just print the shape. Query v.shape, so self.query.white.shape, which will be d by dk, I think. Where? What did I, yeah. 512 by 512. dk is the head dim, so that's fine. And in this case, so apparently, since I have the t here, this linear layer will multiply each thing here and map it to dk, which is the same as d for now. That's just a matrix multiplication. Along all b and all t in each b. So now comes the q by k t. Don't you know that you are a tensor? No self-awareness. But I actually need to transpose on -2 and -1 dimensions. Divided by dk dk square root not like this. Did I save dk? No, I didn't, so that can be k shape size minus 1, so the last dimension. Minus 2. Let's call this, I don't know what to call this W. And we would need to softmax this. There's no triangular matrix because it's not causal. And we will need to multiply it, or actually, so there's self dot value. Print the shape first. So this equals this times self dot value x so the shape, so this matrix stores the pairwise relations between each element in that 16 by 16 grid. The relationships between the d-dimensional latent vectors, and v dot shape, or w2 dot shape, becomes this, and because self dot value is, well, d by d for now because the head dim, but otherwise it's if it's d by dk, that would mean that we project to dk, and if dk isn't the same, let's try with two heads, because I think that in that case this will error much earlier, because the head dim is smaller now. But I mean, that's the formula. What I want to print as well is self dot value dot v dot shape, self dot value dot weight dot shape, self dot value dot weight. It maps from 100. So there are 128 columns to the latent dim. So the matrix itself is the opposite. It's not d by dk or d by dv, but the linear matrix itself is that. So that means as this rod that it applies, come on, it multiplies by AT. That way it makes sense. So this white matrix is dk by d internally. And I need to softmax this. So this W2 has 256 and 128 long vectors in it. So the softmax, if I do softmax, it should be row-wise to all slices along dim, and we rescale them so that the elements lie in the range 0, 1 and sum to 1. So softmax and dim should be 1. This will just, it should keep the whole thing. And the last shape. So V the chip after softmax, it's the same as before. That's cool, and we could see that V or W. So the shape of that again is, so we need the zeroth and the zeroth. 0. Can I index it like this? I guess I can. It's all zeros. Okay, for now, I guess. So attention is 3 linear layers. This is just a naive implementation of it. Very naive. But now then, we have a transformer block with no mask, then encoder. This doesn't work, and now it's time to fix it. That's fine. So what doesn't work is this permutation. Some linear projection doesn't work. Maybe it's this. Nope, it's not that one. I mean, this returns now, fine. I get the attentions. So it might be, it's surely this one. Print x.shape and also print these 5, 12, right? Yes, so the times num heads, and num heads is 4. That's gonna be, yeah, 2000. But that, so num heads is, okay, let's just print x.shape as I did. Now we are printing it twice. So because cat concatenates it along the batch dimension, and then that doesn't work. So I should concat it on the last dimension. Yep. Nope. Same issue, different shapes. So I have 256, this one, and so then it's just 256. I don't think this is D to D. D is 5, 12. It x.shape, so yeah, I mean, this returns, so that makes sense because we split it up here. So maybe D to D will work. It does. Only thing left is this one. This doesn't work. Transformer block has no attribute ln2. Well, it should have, but I made a typo. And now we have some kind of a transformer block. And let me peek if I did it right. Referring back to Andrei's GPT implementation. Well, I don't have a dropout here, I think. That's fine. The feed forward, linear, Kero. Actually, yeah, I remember, and it's in the paper. It scales up to 4 times the embedding dimensions, and it scales back down. So my feed forward is wrong. I don't need a normalization there because I just don't. But one more normalization. That's actually not in the block. So the block is just this. It's a softmax on dimension -1. This I did wrong because I became a math dummy. This is the actual notebook. But then I should multiply this. Yeah. And it's just easier to multiply numbers. It's a less expensive operation. That's why it's on -0.5 and multiply, not divide. So actually in the feed forward block, I should upscale this to 4x and then Kelu and downscale it back, and the dropout was there as well in the feed forward. Yeah, okay, I don't need it anymore, I guess. What now? FF. Great. Now I can bump up the number of layers as well. Okay. Now the decoder because how the video tokenizer works in Genie. Let's check that. We compress videos into discrete tokens to reduce dimensionality and enable higher quality video generation. We again make use of VQVAE, which takes in T frames, yeah, just 1 frame for us. As input, generate discrete representations for each frame, where D is the size of the discrete latent space. Tokenizer trained, blah, 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 blah. So the encoder now outputs this because I scaled it back. So this is a grid of those latent vectors. That will be passed to the vector quantizer, which takes D and the codebook size and receives it like this, but it doesn't care explicitly so much about H and W because it will just squash them to this many latent vectors in D dimensions. Use this identity to calculate the distances from all BHW number of input latent vectors coming from the autoencoder to all K codes. So the codebook white transposed, and we multiply Z, BHVD, and the codebook white transposed is DK, so that becomes BHWK, and of course we have BHW number of Z squareds and 1K number of E2s, and if we add these and subtract these and evaluate this, then we get the distances from all BHW number of input vectors to the K number of that's a lot of numbers, K number of codebook vectors. The codes for each BHW input vectors are the nearest, so where the distance is the minimum and the index of that. We select it from the codebook using this index select. Dimension 0. Let's just be 0 then. On dimension 0, because in E, that's the K. So we select all those d-dimensional vectors in the codebook at the indexes of the code. So this is multiple, this is actually BH number of, BHW number of codebook vectors of dimension D, and we will need to rearrange them into this grid BHW, and then just because the input was in this shape, then we permute and ensure that the memory is contiguous. So realign the memory. ZQ straight through is a trick because this is non-differentiable, and for backpropagation this will work, this wouldn't. Now the codebook loss measures, the codebook loss penalizes. Actually the codebook loss moves closer the codebook, and the commitment loss moves closer the transfer, in this case the output of the transformer, so the encoder's output. So they move closer and closer to each other. By detaching, we can treat this as a constant. This will not be adjusted during back propagation. So the beta defines that the ZEs, the encoder's outputs move at 4 times less the speed as the codebook vectors move towards these. So they move closer together, but at each learning update, the codebook moves 4 times as fast as the encoder's outputs move closer to the codebook. This means, I mean, it makes sense because we want the codebook itself to adjust more to the encoder's output, because the encoder already transformed the data a lot. So it places it in the space much more precisely. We do not want to force the encoder so much to change its output just because the codebook, which was initialized uniformly between these, so we don't want to let this uniform initialization have so much effect on a larger previous network's outputs. So that's the total VQ loss, and with torch.nograd, if we take the indexes for each BHW, so all the vectors in this input, and we take the indexes in the codebook and one-hot encode them, perform a mean, then basically we can get how many vectors from the codebook were used, or how many times each vector in the codebook was used in this forward pass. And this is the formula for the Shannon entropy. P times log P summed in the minus and perplexity, which I treat basically as the codebook usage. It's just entropy exponentiated. And ZQST will be passed to the decoder, which is in the same shape BHWD as, no, sorry, BDHW as ZE, meaning the output of the encoder BHWD will have, the decoder will have the same input, and probably we should do the same here. So I'm not sure if I should convolve here. Because we are not converting these anymore into patches. They are already in those patches. This actually just downsamples and it doesn't change the shape of it. It only changes the number here, the numbers here, but the shape is the same. So then here we have convolution blocks, and we should have a sigmoid in the end. Or maybe some, would a convolution make sense? I'm not sure. But a sigmoid probably. And now if, yeah, great, I would like to see some commentation on the sigmoid. So if I call sigmoid on that shape, should keep the shape, and it will just be applied to this last dimension, I believe. However, our resulting image has 3 channels, so I definitely need a convolution before that to convert it back. So let's take the convolution here, because this is still D dimensions, and from D we convert to 3. Kernel size, I mean, there are different options here. I could set a kernel size 3 with a padding 1 and a stride 1. Try that. So z equals self.conv z, and then z self dot, I would say sig instead, sig z, and this is not needed anymore. Yep, that works. Now let's just try wiring together the encoder and the decoder without the quantizer and just see if it works. Different code block maybe. So I have an encoder. Let's make a decoder. Same latent dim, num heads. That can be like, maybe we can keep it at 4. It doesn't need to be the same. Num layers 3 to the device. We have y hat. That's good. And decode y hat. It's actually, let's call it now z, and decode z, that will be y hat, and this is going to be z dot shape. So something is wrong. Cannot typo again somewhere. So in the decoder there is no z, but this is actually z. Did I fix it here? Yes, because here I apply a convolution to get z from x. Now the issue, torch.layer norm. Where's the layer norm? Layer norm, layer norm. It's only in here. Give a normalized shape, 512, but got a different input size. What's this number here? 16. Okay. A z dot shape. Yep. So if we go to the decoder, This here is actually D num heads num layers. So quickly going to change that. DK num heads num layers. So D and heads and layers. Same here. Yes, that looks correct. The layer norm, going back to the decoder, so this has some issue. Let's print it out. Set the shape, decoder that shape. Decoder Z1, Z2. Z2 is this horribly big number. 16 won't work. 16 D, because in the decoder, so what do you output here? Let's just check. No, the vector quantizer isn't in. So this shape, the encoded Z shape is 116, 16, so 256. That's okay. But then you shouldn't multiply it, because this is batch HWD, and D should come here. D should come there. Probably shaped it back the wrong way. So I definitely did in the encoder. The encoder's input is BD. Yeah, because this is already the, I should have printed this here, because I just got confused. So this batch no, first I should view it as BHWD. So this, then permute it. Now that stays 0. The last one comes here. So D, and then 1 and 2 and contiguous memory. Same applies for the decoder. Yep, now. But, so this takes BDHW, BDHW, that looks good. Wait, where's the decoder? Here. So, can remove and paste here. Okay, 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 okay. Now check if we can place the vector quantizer there. Let's check if encoder plus VQ plus decoder works together. Now it's gonna be 512. Num codes 512 and heads 4 and 4. It's a big one. Okay. Seems to be fine. And let's use the same parameters here. But actually, yeah, 32, I'm going to write it out explicitly to see. So D is 512, K, the codebook size 512, and heads is 4, and layers is 4. 25 million parameters. How big was their video tokenizer? $55 million, 16 seconds video clips at 10 FPS with 160 times 90 resolution. That's the resolution. The final dataset contains 6.8 million 16-second video clips. Yeah, it's a big ass dataset, not 5,000 faces. Results are with the 11 billion parameter model. Okay. So they train a series of dynamics models ranging from 40 million to 2.7 billion parameters. I have all kinds of nightly flying animals around me with an open window. A moth just appeared. I saw some parameter for the video tokenizer. Yes. Yes, okay. 200 million parameters. Okay. Can I even run this model for 10 epochs? Well, that's not the issue here as I see. Okay. Let's check again the shapes of these. Print yHead.shape. That's just gonna be a number. that too. What I need is the image shape. So y hat has a shape of, because I did not upscale it. I need to upscale it. But I mean, creating patches from an image in a single convolutional layer, then passing it down to a series of transformer blocks is one thing, but upsampling in a single layer, I don't think that's going to work. Let's check the decoder. Great. You don't say how you upscale. Well, I could just apply the previous decoder with conv transposes to upsample it, but I created 4x4 patches. And so now the transformer it's interesting what the transformer works with. I mean, it sees everything, those 4x4 patches. So since there is no mask here, it sees the 16x16 both back and forth. That means the input size, if it's 16x16, so I need to upsample it exactly twice. So I don't need a residual block, but this instead of that. So sequential model. Yeah, this is, I'm not sure if I should put maybe output channel 32, kernel size 4, stride 2, padding 1, that upsamples once, there's a relu, dropout disabled, and one more block of this. So it's fixed in the encoder that this will downsample it basically twice at once. Divide the size by 4, so I can use this as a constant 2 layers, but the sigmoid comes here. Not sure if I should use the group norm, but yeah, let's. And the number of groups, 8 output channels. That's not going to work. So that's just it. So I want to explicitly write it also here. So kernel size, stride, padding. So the stride here will actually insert pixels. I don't need the sig anymore, nor the conv. Just the net. Like this. So the encoded looks fine, and reconstructed looks fine now too. Fine. Out of memory. I have 16 gigabytes of memory and 2 video cards, but I would need FSDP or DDP, no, FSDP for this, or maybe deep speed, and I'm just working in a notebook. So let's try to reduce the model size a lot. And oh, that's too much. It's really too much. Okay. And the batch size could be lower too, because it's pretty high. Yeah. I will lower the batch size to 64 or 120. Training is going to be slower than. I can increase the model size if the batch size is smaller, but then the training will be longer. Okay, what's this? It didn't free up the GPU memory, I think. GPU 1. Yeah, memory is full. It just crashed out and it didn't free the memory, so Python is still occupying the memory. I know how to free it up on Linux, but I'm not on Linux. Maybe I could just use the task manager. If I restart the kernel, yeah, you just need to restart the kernel on Windows and it will free up the GPU memory. So 5 million parameters, just 10 epochs. That seems pretty fine, so let's train for 90 or 190 more epochs. GPU memory is set at 5.2 gigabytes, which means I could I would increase the model capacity instead of the batch size, so I can train a larger model. Let's see if this even converges to anything. So we have overall an encoder that accepts 64 by 64 images RGB and have 3 transformer blocks with 4 heads then it outputs a latent E. Then the vector quantizer maps that set E to with a codebook size of 512. This set E is 16 by 16 patch of 256 latent dimensions, and the vector quantizer maps that into one of its codes or tokens. So we have a total of 512 tokens, and the perplexity shows how many we actually use, and right now only 7. of that 512. So there's pretty much of learning to do. And the decoder takes that, so this is going to be basically ZQ, and the decoder takes that ZQ, this is the same 16 by 16 256, and the decoder takes that ZQ, has again 3 transformer blocks, because I just mirrored it, but DeepMind found it that the decoder should be scaled instead of the encoder because it provides better quality. So maybe I'll split and this will have more transformers. So the end result is the reconstructed image, 64 by 64 by 3. Very interesting. Let's run it more. 300. So we run it for, let's run it for 800 steps. And this is VQVAE transformers. I'm curious, this perplexity is really low. Really low. So maybe this is because the data set is really small. Like 10 tokens might be enough to represent all the data. It's all just faces and just 5,370 images. So in fact, this might be a lot. So basically, the transformers can learn it only with 10 tokens. It's also really interesting that they use the fixed learning rate in Gini. It's the same and it's a pretty high number. That's just for the video tokenizer, and again we have an image tokenizer. So just to recap what the transformer does, or at least what I think it does here, is we have these 16 by 16 grid of latent vectors. Basically, first time it's just a single convolution, no overlap, just the image patched into 4 by 4 pixels. And those 4 by 4 pixels that's 16 by 16. The kernel size is 4 by 4. Which means if you divide 64 with 4, that's that, and again that. And for each 4 by 4 patch, this creates 512 numbers, or yeah. Or actually, this is the channel height and width of the image. I mean, basically this downsamples it twice to have a 16 by 16 grid. And this 16 by 16 grid exists 512 times. It's the number of channels. So the transformer block as we reshape it, BTD, that's in total 16 by 16, that's 256 latents of 512, and the transformer compares the, basically, yeah, it stores the correlations between each of those, because with the query and the key transposed, this transposed on -2, -1, so this becomes BDKT, and with this we will have a BTT. So for every batch it checks each pixel in that 16 by 16 grid. Well, it's a latent D, but the connections between that 16 by 16 will be stored in W and then softmaxed by row. Yes. To get basically kind of probabilities. So it's T and T. So each pixel or latent vector in that grid will be assigned probabilities for each of the others. Weights, basically, importance weights, attention weights, even to itself, I think, because there's a number for itself as well in the diagonal. And then that is multiplied. So here this is BTT. This is can this be BTT? Or I am wrong, because this is BTDK. It's a swap, that's gonna be BTT. With softmax. And BTT multiplied by the value dV. So the matrix there was dV to D. I should print this. But if my assumption is correct, BT T, and it should have. The problem is that the value maps to dV, that's head dim. But the output of self.value and not the... So what self.value does is it will output BT and it maps from D to dV, and the matrix multiplication happens on the last two, so this will be B, D, dV. Yep. So this returns BT dV, the attention block, and dV is this. So if we perform this num heads times, then we will, and cat it on dimension -1, this last shape will be D again, so we can project from D to D. That's the multi-head attention, so yeah, that's D, so that's why we can add them together, because D, and this is also D. How much I'm training? 800. Well, it's using more codes, but it's not using enough codes at all and not converging anywhere. It's just jumping around. So the learning rate is probably too high, and we are not forcing it to use the codebook because the encoder and the decoder itself is, I think, smart enough to work with this such a small data set, these faces. On the other hand, that training loss isn't so good. So this model simply doesn't work really good. I will change the parameters. Since it's all faces, I don't think we need, I'm not sure, maybe a latent dimension of 16 and one layer would be enough. Or just train it forever. Okay, utility functions. This was the VQVAE. I mean, the quality itself, the edges and everything, it's much better. It's blurry, but look at that. With weight decay now. Let's make this 512, but this much smaller. Num heads to layers 1, just one transformer. That's just 170,000 parameters. Codebook use is growing. That's good. Should I penalize low perplexity to make it use more of the codebook, or at least faster? I could do that by, so here's the perplexity, the reconstruction loss. So I would add as perp loss would be 1 minus the k 512, so just simply like this. So 1 minus the percentage of use, but yeah, so this would be 0 if it uses all, and the loss would be negative. I should make this torch.apps absolute. I want it to use around 500 and not more. So if this is small and this term is large, if this goes above 500, this will be a small negative and this will be positive after all. So 27 is used now, and it is worse, but the model is just 170,000 parameters. Let's try making it train with the new loss 400 epochs. I think it can't really figure out. This is also not differentiable. Just use the MSC also here. Yeah. This should be a torch dot tensor. No, it doesn't work like that. It's not like you can penalize it for anything. So if I just don't penalize it, it will still grow. I want perfect reconstruction. Let me just bump up the batch size to 56 with this small model. It should still fit in the GPU. Didn't even increase VRAM use. It's only the model. Because these are such small images, the whole data set is small. So if I just have one head and 64 or 32 dimensions, but 4 heads and 4 layers and train for a, I can't stop it, that's the issue. So while that is training, 300,000 steps, 8 heads, 12 layers, but this is this is able to generalize to 30,000 hours of videos, and it also works with videos, so a sequence of frames. So actually, to extend this, so this is basically like an image transformer if I implemented it somewhat correctly at least. And for the temporal transformer, I would need to reshape. I would have another dimension actually, and this would be called not t but n. That's the proper naming here, n, because it's not time. And then I would have a t, so it will be bt n d. In that sense, I wouldn't have h by w grid of these, but a cube of these, t by h by w. And for this image transformer, the spatial transformer, this would be that, I think. And the other would work on the t dimension, so anyway, I won't be able to figure that out now. Okay, how does this look like? Contrasty, interesting, with binary cross entropy. Can we get it to work? But I guess not really. Kind of stalled here. I'm interested in the tokenizer loss function. The latent action model is trained with the cross entropy loss. The model is trained with the cross entropy loss between the predicted tokens and the ground truth tokens. That's the dynamics model. Why don't you write it for the video model? Okay, one more try. What if it's mean squared error, but the reduction is sum? I achieved much better results with the variational autoencoder with the sum, which is not anymore mean squared, but could try adjusting the beta as well. I could try adding dropouts. Is the training loss growing? Yep, it's definitely exploding. Nan. Okay, fine. So nope, not here. But the dropout is there. And maybe I could also just up this to 128. Okay, you can stop now. And layers enc and layers decoder and layers decoder and layers encoder 2 4 num heads 64. Let it be 3 might work. And layers and okay. This won't work anymore now. Layers and okay. Run. What? Yeah, because D I think numheads 1 would be enough for this small set. It's blowing up again. It's just worrying that the perplexity doesn't... So D was... Let it be 256. 300 epochs when this finishes, and if it finishes conclusively somehow, wow, it converges, but the jumps are huge. Maybe now. I'm just going to leave this for the whole night, see where it goes for 10,000 epochs. However, in that case, I want to auto-save it and track the min loss. And if the average test loss, so the min loss will be float inf, and if the test loss dot item smaller than min loss, then save the model. The entire model and print min loss test loss model saved min loss equals test loss dot item, because that is a tensor. This is kind of odd behavior. I think it should by now learn to, these jumps are really big. I mean, it will be interesting to see what it does after 10,000 epochs, but I don't think, it's just blowing up basically. It's not really finding the sweet spot. Perplexity could grow till 500. But it's just dropping back. Maybe an implementation error or my shallow understanding of what's going on. Maybe the group normalization, or I fucked up the attention. Or this part, which is just hypothetical. This is not converging anywhere. So make it huge. And the learning rate. Okay, let's see. Let's see tomorrow